Welcome back, everyone. Now that we have wrapped up linear functions and plotting lines, we will talk about some similar aspects of quadratic functions. The standard form of a quadratic function is y equals ax squared plus bx plus c, where the a, b, and c are the coefficients of the quadratic, or the square term, the linear term, and the constant, respectively. Recall when we first discussed plotting the curves from these equations, quadratic functions give these U-shaped curves, which are called parabolas. First off, let's see what the base parabola looks like. This is the curve that generates from plotting the equation y equals x squared. There's no number written out in front of the x squared, but there's an implied 1 here, so the a is 1. There is no linear or constant term in this equation, so the b and c are both equal to 0. You can go through and plot some points on your own, but we will see the general shape of this parabola from x squared looks like this, where the bottom of this U-shape is located at the origin, and we call this lowest point the vertex. We also say the graph opens upwards. As the values of a, b, and c change, the curve would move around, become more narrow or wide, but the main thing we want to pay attention to right now is what direction the parabola will open. It's actually quite simple. If a is positive, or greater than 0, the parabola will always open upwards. And so we'll get something that looks like that. If a is negative, however, or less than 0, the parabola will now open downwards and look something like this. And so we can know which direction the parabola opens just from quickly looking at the coefficient of the x squared term. In both of these cases, that little tip of the u is always what's referred to as the vertex. So depending on which direction our parabola opens up in, our vertex is always either the lowest or highest point. For parabolas that open upwards, the vertex is always the minimum. While for parabolas that open downwards, the vertex is always the maximum. Let's go into a bit more depth on the vertex. Since the vertex is always either a minimum or maximum of the parabola, it's a very useful tool for many types of problems. Because of that, we will want to know how we can calculate it. We typically labeled the ordered pair of the vertex as h, k, h being the x-coordinate and k being the y-coordinate. Getting these coordinates of the vertex can be helpful when plotting these parabolas, as we immediately get the point where the shape starts, and as mentioned, is very useful in a variety of problems. Fortunately, there is a fairly simple way of getting the vertex from our equation. If we have our quadratic function in standard form, ax squared plus bx plus c, then the x-coordinate of the vertex, the h, will just be given by negative b over 2a. Once we find that x-coordinate, finding the y-coordinate, which we labeled k, is simple as plugging in h for the value of x. Because getting y-coordinates from our functions just involve plugging in the x-coordinate of the point. Let's go through an example. Consider this function here, y equals 2x squared minus 8x plus 5. Let's go ahead and read off what our a, b, and c should be. The a is the number in front of the x squared, which is 2. The b is the number in front of the x, which is negative 8, because in our standard form, the b usually has a plus in front of it, and our c is the 5. If we want the vertex of this parabola, first we will calculate the x-coordinate, the h, as negative b over 2a. Plugging in the appropriate numbers here, we'll have negative b is negative 8, over 2 times a is 2. Negative negative 8 is just 8. Divided by 2 times 2 is 4. 8 divided by 4 is 2. So the x-coordinate of our vertex is 2. If we want the y-coordinate of our vertex, the k, that will be just what we get when we plug in 2 for x. So anywhere in our equation we see an x, just replace it with 2, and we'll have this. If we go through and do the math, we'll have 2 times 2 squared is 4, minus 8 times 2 is 16, plus 5. 2 times 4 is 8, minus 16 plus 5 still. 8 minus 16 is negative 8, plus 5. And from this we'll get negative 3. And so our vertex is located at 2, negative 3. Once we have our vertex, we can quickly see the general idea of what this graph will look like if we were to plot it. 2, negative 3 will give us a point somewhere in this area. Then if we look at the a to determine if we're opening up or down, our a is positive 2, so we should be opening upwards. So our graph should look something like this. Now obviously this wasn't very precise, but it can help you quickly visualize what the graph should look like. While we are discussing the vertex, let's also introduce another form of the quadratic function called vertex form. This vertex form will let us quickly read off the coordinates of the vertex, or if we already have the vertex, we can quickly write this form of the equation. The vertex form looks like y minus k equals a times parentheses x minus h squared, where the h and k are again our coordinates of the vertex as we defined earlier, and the a is the same a as in the standard form. So if you were given an equation in this form, you could quickly read off the vertex as h, k. But let's see what the vertex form of our previous example would look like. Our vertex was 2, negative 3, so y minus k, the k is the y-coordinate, so negative 3, equals the a we can just read off as the same a that's in front of the x squared in our standard form. So 2 times parentheses x minus h. H is the x-coordinate of our vertex, so 2 squared. We'll go ahead and change this subtraction of a negative to addition. And here is our vertex form. This is the same equation and gives the same graph as our standard form example, but is just written in a slightly different way. As mentioned earlier, another prominent use of the vertex comes from the fact that it is always either the minimum or maximum of the parabola. So if we have a problem where we are looking for some kind of minimum or maximum and end up getting a quadratic equation, our answer will simply involve finding the vertex of that equation. For an example, consider we have some rectangular field with unknown dimensions given as shown here. This bottom side, and therefore the top as well, are defined as x, while the left side and right side are defined as lengths for minus x. And the question here asks us to find the dimensions that maximize the area. When trying to minimize or maximize something, we always need the equation related to that quantity, so we want an equation for the area. The area of a rectangle is just going to be the length times width, so the two sides here multiplied together will be x times 4 minus x. If I go ahead and expand this, I'll have 4x minus x squared, which I will rewrite slightly as minus x squared plus 4x. Now I have a quadratic equation for my area. Note that because of the minus out in front of the x squared, if we were to graph this parabola, it would be opening downwards. So the vertex here would be a maximum, which is consistent with what the question is asking for. The x's are related to the dimensions of the box, while the y's on a graph would be the area. Now that we see we have a quadratic function and are looking to maximize it, we will calculate the vertex. The x-coordinate will be h equals minus b over 2a again. In this case, our b is 4, so we'll have minus 4 over 2 times a. In this case, a is minus 1, so we end up getting minus 4 over minus 2, or 2. So area is maximized when x equals 2. If we wanted to find what the maximum area was, we would plug this 2 into our area equation. But this question was asking us to find the dimensions that maximize the area. Well, we just saw that the area is maximized when x equals 2, so this side that's just x has to be 2. But we also need to figure out what the 4 minus x side should be. Well, that's as simple as just plugging in 2 for x. So this side should also be 2. And so we end up with a 2 by 2 square to maximize this area. As you can see, the vertex is a prominent part of quadratic functions, being very useful when dealing with finding minimums or maximums. Until next time.